Oh, she's coming back. Okay, cool. Oh, Sam was looking for you earlier. Oh.
Okay, good evening, everyone. I'll ask you to come in and take your seats. Okay. Good evening, everyone. My name is Richard McDermott. I'm a professor of astrophysics here at Macquarie University and director of Australian Astronomical Optics, which is a specialist research and engineering group here at Macquarie that builds instruments, software, and data systems for the world's largest telescopes, something that we're going to hear a lot more about this evening. I'd like to begin by playing Macquarie University's Welcome to Country.
Welcome. We acknowledge the traditional custodians of Macquarie University land, the Wadamadigal clan of the Darug Nation, whose cultures and customs have nurtured this land since the Dreamtime. We pay our respects to elders past, present and future. We welcome people of all nations and all faiths. Kwai Bidja, Jamna Payala Janawi. Come here, we speak together. We have 60,000 years of archaeological evidence of Aboriginal habitation at Lake Mungo and 20,000 years in Ryde. We have great antiquity. Today, hundreds of Aboriginal and Torres Strait Islander people graduate from Macquarie University. The Darug Nation had famous leaders such as Chief Yarramundi, Naraginji, Colby and Maria Locke. Many of the descendants of these Darug people live today amongst you. We celebrate with you our ongoing attachment and custodianship of this country. We celebrate the achievements of Macquarie University.
Inspiring words there from Darug Elder Auntie Julie Jansen. And I'd like to add my own acknowledgement of the traditional owners of the land we're meeting on this evening, and first astronomers of this land, the Wallamadigal clan of the Darug Nation, whose customs and traditions have nurtured this land and the sky country above our heads since the Dreamtime. And I pay my respects to elders past and present and extend those respects to any Aboriginal Torres Strait Islander people here in the audience tonight. Welcome, everyone. This is a wonderful turnout for this first installment of the 2026 Discovery Lecture Series from Macquarie University's Faculty of Science and Engineering. This series of lectures highlights the impactful research conducted within the faculty and allows our staff to share the spirit of discovery, creativity, and innovation that's at the heart of this university. It's also my great pleasure to introduce this evening's speaker, Nuria Lorente. Nuria is a co-lead of the Research Data and Software section and head of the Software Engineering Group at Australian Astronomical Optics. Her 25-year career has taken her around the world, from CSIRO's Australia Telescope National Facility to Georgian Bank Observatory and Astronomy Technology Centre in the UK, European Southern Observatory in Germany, and the National Radio Astronomical Observatory in the USA. Nuria has worked in a number of high-profile projects and instruments, including leading the development of the science data model on the ALMA, that's the Atacama Large Millimeter Array telescope in the Atacama Desert in Chile, instrument and data simulations of the famous James Webb Space Telescope and MIRI instrument aboard that telescope, and leading the development and maintenance of data pipelines for the European Southern Observatory's instrument suite in Chile. More broadly, Nuria is a leader in the international astronomy software community and a champion of equity, diversity, and inclusion in her field, serving on committees both nationally and internationally. And we're very lucky to have Nuria talking to us this evening. And as a fellow astronomer, I'm particularly excited about this talk, which is entitled Decoding Our Colourful Universe, Rainbow Fingerprints, Spectroscopy, and Data Curation. Over to you, Nuria.
Thanks so much, Richard, for that warm introduction. Welcome, everybody. I'd like to start by saying those of you who had tickets to the talk I was scheduled to give last July, only to be told at the last minute that it was cancelled a couple of days before. Thank you for your patience and understanding and for rebooking and coming tonight. My father had died a few days before and his funeral was on the day of the talk. So obviously it couldn't go ahead. From an early age, my dad encouraged me to read widely, to ask questions and to look for answers. And his dream was that all his children would get the education that he couldn't have. So I would like to dedicate this talk to him. So I'd like to start with a beautiful image. The Orion Nebula at the top right, and the Horsehead Nebula at the bottom left. This image was taken by David Malin. He's a now retired AAO staff member who was a pioneer. He essentially invented astrophotography. He developed many of the techniques that bring out the color and the detail in image plates. To put you in context, this observation was taken in 1979 using the UK Schmidt telescope, which is located near Coonabarabran in northwestern New South Wales. And this version of the image was put together in 1987. This will become important later. Let's zoom in a little bit. Let's look at this beautiful detail. If you're curious, this image, the larger image, was taken using the same plates as the previous wide field one. What do we know about the beautiful nebula itself? So it formed from a collapsing interstellar cloud of gas and dust, and it glows because it's lit up by a nearby star. Let's jump forward in time a little bit. Same area. We're jumping forward to 2024 and going into space. Let's see how the James Webb Space Telescope captured the same region of space in infrared light this time rather than in visible light. So infrared light shows us things that are warm and hot, and this allows us in this instance to see space dust, which we can see here in lovely detail, much more than in the previous visible light image. Coming back to Earth for a moment. Astronomy images are everywhere. They're ubiquitous in modern life, they're beautiful, and they give us a sense of wonder, so we put them all over the place. We put them on walls, we put them on screens, on mugs, on puzzles, on doors, on furnishings, on all the things, even on ties. I would love to see somebody with a space-themed bow tie. On socks, skateboards, even shower curtains. Anyone for a shower curtain with an astronomy image on it? So why do we find them beautiful and all round interesting? And what are we really seeing when we look at this, apart from a beautiful image? When we're looking at those colors in particular, are they telling us anything beyond how magnificent the universe is? So over the next little while, we're going to go on a brief journey through color and space via a technique called spectroscopy, which is what we use to find out a large amount of what we know about the universe. So we will then come back to Earth and look at the surprising use of spectroscopy for Earth-based detective work. And finally, we'll look behind the scenes at the data and software engineering that allows much of this to happen. So first of all, how do we get these images? Let's talk a little bit about telescopes. What are they and why do we need them? You wouldn't be here if you didn't have some idea of what a telescope is about. But isn't it enough to go outside and look? It's a good start, but as you all know, our eyes are not really good at collecting enough light to see the faint detail of the universe. So at its most fundamental level, a telescope is a tool for collecting enough light from your object of interest so that we can see it and we can study it. So those of us in astronomy, particularly in instrumentation, often nickname telescopes light buckets, because that's what they are. I brought one with me. Here's my bucket, or telescope tube. We need a reflector, something that will respond to color in the way that, in the region of the spectrum that we're interested in detecting. In my case, I want visible light. Tube, this is my mirror. Does it look like a telescope yet? We then need a waveguide. What's a waveguide? It's a fancy term for a tube. A tube that will take the light that my telescope has collected, and send it off. Can you all see if I put it there? Let's put it there. Send it off into a camera. I have a camera. There we go. How's that for a telescope? All right. So that's really not going to make any groundbreaking discoveries, is it? And it's not going to win any astrophotography prizes. But here are some world-class telescopes that actually do both of these things. So when I say telescope, most of us think of optical telescopes, right? Like the Anglo-Australian telescope. Do I have a pointer? All right, I'm going to point. Anglo-Australian telescope, up in the middle in yellow. No, that's not, I'm not tall enough. How about here? Can you see the pointer now? Haha, there we go. Right. So we tend to think of optical telescopes like the AAT, the Anglo-Australian telescope at Siding Spring Observatory, which is near Coonabarabran in northwestern New South Wales, or the UK Schmidt telescope on the same mountain, or most magnificently, the European Extremely Large Telescope, which is in the process of being built. And they are sort of like that in that if you took the detector out, if you took the camera out and you put an eyepiece in, you could stick your eye up against it and see something through it. It'd probably burn your eye out because they are pretty impressive light buckets, but you could in theory do it. But there are telescopes that look at the invisible parts of the spectrum. So many of you will be familiar with the dish, the Parkes radio telescope, the Australia Telescope Compact Array, which both of which are in New South Wales, or the Square Kilometre Array that is being built in Western Australia. So that's over in the radio, a different colour that we cannot see. Then between radio waves and infrared waves sit submillimeter waves, and the ALMA telescope is able to observe that colour. And over in the infrared, which I mentioned before, is the James Webb Space Telescope, out in space at the second Lagrangian point, doing its thing quite fabulously. And looking beyond at X-rays, so looking at the universe in X-rays is the Chandra telescope in space, and all the way at the very high energy regime, we have gamma rays, so the MAGIC telescope in La Palma. I love the fact that they called it the MAGIC telescope. And the Fermi Gamma Ray Observatory, also in space. All right, so now we know about telescopes. But between the light bucket and the camera, there's often precision instrumentation that is necessary to get the light from one to the other. Sometimes it's the pipe. How do we get the light from one place to the other? Sometimes it's complex optics. Here at Macquarie University, we have world-class experts that design fiber positioners, which are robotic instruments that very accurately place hundreds of optical fibers into the telescope's field of view. And that allows us to catch the light of individual stars or galaxies and carry this light into the instruments, into the cameras, which may be in another part of the observatory. So I have two different types of these here, which you can see in some of the images. This one has a wonderful name. It's called a starbug. You can come and have a look at them later. It's a tiny little robot which has a piece of optical fiber. The robot moves around and puts itself into place. The other end plugs into a long optical fiber that sends the light into a spectrograph. We're going to be talking about spectrographs in a minute. So we have 300 of these. They all move at the same time. And it just allows us to do science faster. Sad thing about these robots is that this is a project that we stopped working on. Sometimes in science and technology, you spend 10 years working on something and discover that actually to get this to work really, really well, we would need to spend a lot more time and a lot more money. And we make a decision to say, okay, let's put this back on the shelf for now. We might come back later on and continue with this when maybe some technologies have moved ahead and we can do it with less expense and less time. So that's not currently doing science. This, however, very much is. So this is the same sort of principle. You have an optical fiber, which you can't see, but I can. I'm not just waving my hand, there is a fiber there. And a carbon fiber tube, and the fiber goes all the way up to the end. And you have a whole army of these. In the instrument that this is in, it's more than 1,000. So you have 1,000 of these, and they move independently. And what that allows you to do is similar to the starbugs. It allows you to capture the light from 1,000 different objects at once. And the light from those comes down the fiber over into another room. Why do we want to send them into another room? Because the instruments that this light goes into to break it up into its different colors, the detectors that are used sometimes need to be refrigerated, and you're not going to put an enormous fridge on the telescope. Or the instruments are huge, and similarly, you can't put them on the telescope. So we put them somewhere else, often in rooms that are very tightly controlled in terms of temperature and vibration, dust, anything that could upset the finesse of the instrument. And these fiber positioners do the work of carrying the light to there. So this is something that happens here, that there are colleagues in the room who have worked on this. Maybe you can meet them afterwards and have a chat about fabulous astronomy robots. So let's go back to some pretty astronomy images. Back before digital and into the analog world. I say the analog world, but it wasn't that long ago, right? I'm not talking about Galileo and Newton, but analog astronomy within my lifetime. And I'll take exception to anybody who mentions that I'm ancient. As an example, in the 1970s and 80s, significant astronomy studies were being carried out at the UK Schmidt telescope, which we've seen before today, using photographic techniques to capture highly detailed images of the sky onto glass plates. Now, you can see some examples here. You can see them on the image, same piece of sky, The top one was taken through a blue filter. The bottom one was taken through a red filter. There will have been a third one taken through a green filter. And when you put these three together, you end up with the beautiful colors of the images that you see. I was asked earlier today whether, because we put images together in post-processing, are they fake? So I'm going to show you how they're not fake. I can understand why people say this, but they're really not. So let's see. Ha, magic. All right. This is a plate. This is a real plate, 3 millimeters thick. It's actually not the one that the telescope took the photo with. Right? This is a copy. The real ones that were on the telescope are only 1 millimeter thick, and they live in climate-controlled plate library, and they don't give them to me. This is a copy, but nevertheless, the copies are what we used to use to very carefully look for stars and galaxies. And in fact, I think I may have spotted a galaxy. So astronomers used to sit with loops and look at these very closely and look for, can I see any edge-on spiral galaxies? Can I see any face-on galaxies? Painstaking work that took many, many months. I also have, and I'm going to hand these to my two happy assistants. Thank you. So these are acetate copies of the same thing. Please be very careful with them. The glass plate is mine, but those two acetate ones are borrowed, and I really don't want to have to explain what happened. So have a look at them, hold them up to the light, see if you can see any stars or galaxies on them. So each of these plates contains hundreds of pieces of information. And you can see there, you know, a very small portion of the plate. When you blow it up, you can see there's a fabulous spiral galaxy there. So back in analog times, once they had made a discovery, of course, astronomers would want to tell their colleagues in other parts of the world. And often this would be done via something like this, an International Astronomical Union circular issued by the Union's Central Bureau for Astronomical Telegrams. And these would turn up in the post, like a Christmas card. This is the only one I was involved in, on the 7th of July, 1995. Why am I showing you this? Because communication was slow, which meant that quickly following up on a scientific result was very difficult. So what has changed? And why? And is this a good thing? Telescopes and instruments have become much more complex. And with the proliferation of telescopes that see in all the different colors, we want multiple perspectives. You no longer have optical astronomers and radio astronomers and X-ray astronomers. You just have astronomers, because it's really important to see objects across the entire color spectrum. And that also means that science and technology has become a lot more collaborative. So astronomers need to work with engineers, need to work with data scientists, and collaborations appear across countries and institutions. Also, the data are understood to be expensive, because telescopes are expensive, people are expensive, which changes our attitude towards data a little bit. And there is now a well understood expectation that data will be used not just by the scientists who proposed that observation at the telescope, but used again and again by astronomers all around the world. which is why that 1979 image I showed you at the beginning, the photo that I showed you was actually produced many years later, because the data is reused. There is still interesting science to see in there, particularly when you bring in more modern instruments to combine with the old data. So projects are now collaborations of individual scientists and engineers and collaborations of institutions and countries. And our need to facilitate and improve our ability to collaborate at all levels has grown, which I love because I'm a team person and I love doing things with other people. So astronomy is no longer really a single individual endeavor, but it's a collaboration at a technical level, at a data level, at a human level, at an institutional level. Let's look at some more pretty pictures. Let me share with you this image of the Sombrero Galaxy. This was taken with the Anglo-Australian telescope by David Malan in 1993 using visible light, which I've marked in this key in the bottom right. It shows the spectrum and the visible portion is highlighted in yellow. So the Sombrero Galaxy is named after the Mexican hat that it sort of looks like, if you squint slightly. It's one of the most famous galaxies in the sky, and it's in the Virgo constellation, if any of you know where that is. It's an edge-on spiral galaxy, we can see that. And you can see the billions of old faint stars that form the bulge of the galaxy. And you can also see the, oh, I'm sorry, I haven't turned that back on. Sorry. There we go. You can also see the dust at the edges of the galaxy's disk. So from 1993 to 2004, this is another visible light image, this time taken with the Hubble Space Telescope. What has changed in that time? You can see more detail, and the image is cleaner. So now we move from the light that we can see to infrared light. Anything that's warm gives off infrared light, which we see in daily life with an infrared camera, mostly in movies, but sometimes in real life. The James Webb Space Telescope's MIRI instrument is an astronomy version of that sort of heat camera. So what's different in infrared? Well, it no longer looks like a hat. The bulge of old stars has gone, but what we can see is the clumpy nature of the dust along the galaxy's outer ring. So the mid-infrared light highlights the gas and dust that are part of the star formation that's taking place in the outer disk. Interestingly, the rings of the Sombrero Galaxy produce less than about the equivalent of one of our sun's mass of stars in a year, in comparison with the Milky Way, which produces about 2 solar masses per year. So it's not a particular hotbed of formation of new stars. So moving on to the radio regime. So if you remember, this is taken the radio telescopes like the Parkes telescope. This is taken by the Very Large Array in New Mexico in the US. And this image is from a paper by Yang et al. In 2024, so it's very, very recent. And it shows us that there is a jet in the region of in the color of the spectrum, if you like, that we can see at 1.5 gigahertz. You can see a jet north and south of of the galaxy. And finally, this is what the sombrero looks like in X-rays. So this was taken by the Chandra telescope in 2001. And what we see here is hot gas in the galaxy and point sources that are a mixture of objects within the sombrero, as well as some quasars in the background, so that are sort of behind the galaxy itself. So that leaves us with lots of questions. We've now seen this galaxy in lots of different colors. But I would like to know, what are the stars and galaxies made of? How hot are they? How far away are they? How fast are they moving? Are two galaxies that look like they're neighbors, are they actually close to each other? Or is one in front of the other and we just can't tell? They look like they're neighbors. Sadly, we can't get into a spaceship and go and take a sample of gas, or take a ruler to measure the distance, or go to the other side of the galaxy and take a picture from there to get a different view, as much as that would be fabulous. So interestingly, this isn't a new set of questions. In 1842, Auguste Comte, the philosopher, in his The Positive Philosophy work, said, of all objects, the planets are those which appear to us under the least varied aspect. We see how we may determine their forms, their distances, their bulk, and their motions, but we can never know anything of their chemical or mineralogical structure, and much less that of organized beings living on their surface. This is 1842, so these questions have been around for a very long time. So what do we have? Apart from giant rulers and spaceships, we have the light that travels from the objects to us. And we have curious, hardworking people who ask, why is that? And how can we find out? So engineers and scientists who, since the days of Isaac Newton, have been working on improving the technique of taking light, breaking it into its component colors, and measuring and analyzing them to learn something about the object. So light is an information carrier, and spectroscopy is the technique of taking that light and forming it into rainbow fingerprints that tell us about the elements that make up the object that the light is coming from. So I'm going to show you a little video about rainbow fingerprints. What are they and how do we produce them? So we have a star somewhere in the universe sending its light towards the Earth, and eventually it will hit the 4-meter mirror at the Anglo-Australia telescope. It comes into the mirror, goes into one of these optical fibers, down the fiber, and then into some complex optics that breaks the light into its component colors. So you can see the beam of light there. It hits a mirror, bounces back, and then goes into some more optics, and then a prism that breaks each ray of light into its different colors. It goes through some optics to collimate it and make sure that we don't lose any of the light, and eventually it hits a detector. But the light has now split up into its fingerprint colors. And so it no longer looks like a picture, it looks like a series of lines. And by looking at those lines, we can work out what the object is made of. So, light as an information carrier. You've all seen fireworks, and fireworks are pink, and they're white, and they're green, and they're blue, and mixtures of these. Why is that? Because when we take particular elements and we set fire to them, they give off light in a particular color. And the reason for that is because each element has that color signature. Who has seen a periodic table before? Yay! I was hoping all those people in school uniforms were putting their hands up. The periodic table is how we organize for our own minds how the elements in the universe, what their structure is like, from the lightest element to the heaviest. So each of those elements has got its own fingerprint, and this is the rainbow fingerprint of the lightest element, hydrogen. So you can see down the bottom here, I have put the wavelength of the light and the full color spectrum, and then you have the lines that belong to hydrogen. There are more, but this is a small portion. Helium has a different signature. Can you see that at the back? Ish. Iron has lots of lines, gold, and so we can take this information and use it to work out, for example, what's in the sun. So if we look at it, take its light, break it up into colors to produce the spectrum, we can see that it shines in almost every color in the visible range, but the brightest is the yellow and green part. Now the dark lines are from gas at the sun's surface, so in the sun's atmosphere, which absorb the light from the layers underneath. And now that we know that different elements have different spectral fingerprints, we can determine what gases make up that atmospheric layer of the sun. What applies to our nearest and dearest star can also be applied to distant stars and galaxies. So we see here that we compare the lines that we've measured in the lab, so the fingerprints we've measured in the lab for hydrogen, helium, all the elements, and compare that with the sun. We determined that the sun has 75% hydrogen, some helium, a little bit of oxygen, tiny bits of carbon, even smaller bits of neon, iron, and so on. So by precisely measuring the color of light from the universe, we can answer questions about the composition and the evolution of objects in the sky. So temperature and composition. We said before that all objects emit light in a way that depends on their temperature. We can see that in the infrared and with nighttime cameras. And as an object becomes hotter, the color where most of the light is emitted becomes bluer. For those of you studying physics, we call this blackbody radiation, and it applies to all things. So very roughly, red stars are cooler than blue stars, which are cooler than blue-white stars. And so we can use this to identify elements in the stars. And what you see here, and I'm slightly showing you this picture because I think it's an excellent picture. On the left is the Southern Cross and the pointers, and you can see quite clearly that some of the stars are very blue, some are quite red. This image on the right is the same field, but instead of the telescope tracking, they didn't track the sky with the telescope. They let the stars drift, so it produced a star trail. And as it was drifting, they also defocused the telescope. So that produces those beautiful cones. And the great thing about those is that you can see the color a little bit better. That was just because it's a lovely image. So identifying elements in the star. This on the On the left is a spectrum of the sun. You can see the black and white stripe at the top. That's the spectrum. The bottom blue image is how we like to look at spectra when we are studying them. So plotting them as a graph allows us to see not just the wavelength, so the color of the light, it also allows us to see how strong that light is. And so therefore we can measure it. So from this particular spectrum, it's only a small portion. Remember the spectrum I showed you before that had stacks and stacks of lines. From this small portion, we can tell that the sun has iron in it, which are these iron lines. It has lithium in it. I'm going to believe the person who wrote this paper. There's another iron line, some more iron, and a big calcium line. On the right-hand side, we see a similar thing, spectra of 4 different stars. They're just stacked on the same graph so that we can compare them. But you can see that these lines all match, right? So it's the hydrogen in a pile of different stars. All right, I have to apologize. I meant to change the colors of those lines because when I'm talking about colors and then I say the green one, let's pretend they're all gray. The top one is a very hot B star. And so it's around 35,000 degrees Kelvin, and at that temperature, the hydrogen lines are not very bright, but you can see the black body slope, which means the background temperature of the star. The second star is an A star. And it is not as hot. Moving down to the G-type star, it has very weak lines. It's very cool, but we can still measure the chemical composition within the star. Another thing we like to measure is how far away are things, and we use the rainbow fingerprints from a spectrum to tell us this. The bottom spectrum is a lab reference of a particular element. And you can follow these very marked black lines here across stars that are nearby, galaxies that are nearby, distant, and very, very distant. So by looking for those fingerprints shifted more into the red, we can work out how far away the object actually is. And finally, we can measure rotation in galaxies. We can see galaxies rotating. Of course, we can't see that in real time, but we can see by measuring where these spectral lines are, whether the lines have been shifted into the red or more into the blue, that the galaxy is actually rotating. So we can tell all these things without leaving our offices, which is fabulous. So we do all of this for astronomy, and we love astronomy. That's what gets us out of bed in the morning. But why should you care? Why should you care about spectroscopy? We can bring it back to Earth and do interesting things with it here, because after all, the same stuff that makes up galaxies and stars makes up our Earth. We have hydrogen here, we have carbon here, we have iron here. So we can use the spectroscopy technique to work out where things have been grown, for example. Spectroscopy gives us the terroir of objects. So if you have, imagine, your favorite astronomy t-shirt, with the Horsehead Nebula on it. And you have paid large amounts of money for it because it was grown in Australia. You want to support Australian farmers. It was grown organically. It was done with a particular process. How do you know this? Because it says so on the label. I'm a very trusting person, but I trust science more than labels. How do we know? We can take a sample of that cotton from your t-shirt and we can do spectroscopy on it and we can get its rainbow fingerprint. The rainbow fingerprint of the minerals in the earth that ended up in the cotton itself. We can then take that rainbow fingerprint and we can take one from a t-shirt that was made somewhere else with a different type of cotton, a different process, maybe cheaper process. When we have those two samples, we can then take an unknown t-shirt that has been marketed as a super duper amazing Australian grown organic t-shirt and compare the fingerprints and work out whether you've paid good money for a fraud. And this isn't theoretical. This is actually happening. There is a company in New Zealand that specializes on spectral terroir of objects, and there's one in Scotland that does so as well. I imagine they're appearing in lots of places. As products become exclusive and expensive, it's not just consumers, but it's also the people who sell this to the public, the people whose companies they are, who have relationships with the farmers who provide them the cotton, or the companies that provide them the dyes, or honey producers, spices, and so on. It's in their interest to know that they are buying the thing that they think they are buying. So let me show you an example. Olive oil authenticity apparently is a big deal. I always just read what it said on the bottle. There is an industry standard spectroscopy method in the ultraviolet and visible that measures the absorbance of specific colors of light. And, you know, if I said this spectrum was a star, you'd believe me, wouldn't you? Because we've just seen lots of things that sort of look like this. But that's the spectrum of olive oil. Let me show you. These are 3 different olive oils. So the top one is extra virgin olive oil. The middle one is blended oil, so 90% sunflower oil and 10% extra virgin olive oil. And the bottom one is just straight sunflower oil. So there have been investigations and court cases where people have found that their olive oil was not really the extra virgin super duper top line, but the middle one, which meant that it was actually a blend of cheap oils and expensive ones. So this has been done with honey, it's been done with cotton, and more it's done with things that are expensive. So let's look behind the scenes a little bit at how all this stuff happens. We talked about the telescope, instruments, detector, but what happens then? The challenge that we have these days is we have massive volumes of data. We can no longer sit and stare at photographic plates for weeks at a time to do our science. The data that the telescope collects goes into large data stores, and then is, I'm going to say transported, but it doesn't come in a truck. Although I have once transported data in a suitcase by carrying large numbers of tapes. But optical fiber into a data center. This data center that you see here is in our new shiny building down the road. Once the data is in there, the most important part gets plugged in, which is a group of very talented people, some of whom are over there, if you want to talk to them, whose job it is to make the data rigorously available to astronomers and, as we'll see, other researchers as well. And then make it ready to be used by researchers around the world. This is done by a project that we have here called Data Central. And let me tell you a little bit more about it. The aim of Data Central is, well, a Data Central is a research platform and a data archive that's based here. And its aim is to facilitate cutting edge research. And it's made up of many different parts. The telescope produces data. Telescopes produce data, and they have a data archive. The data goes to astronomers for data processing. And either from a raw perspective or from a process perspective, they come and talk to us and say, we would like to make our data available to people. Our data are too big to process on my little laptop. Can you help us? So we go through a process of data curation, which is all about ensuring that the metadata in the data is accurate. So what do I mean by metadata? Have you ever been sent a photo by somebody, a photo of when you were a child perhaps, and it turns up on your phone and you look at it and it says taken in 2025 rather than when you were 5. That is an example of metadata gone wrong. That's fine if it's a photo of you as a baby because you know, but it's not fine when it's about astronomical data. The facts of when the data were taken and how, so what filters were used, what telescope was used, is crucial to get right if we're going to get the right science out. So this is why data curation is super important. And then what we provide is a data central archive where we store mostly science data rather than raw data, although we do have some raw data as well. And we provide services for people to find the data. I took some observations 3 years ago. I would like to process them again. Can I please find them and have them? Or query the data. I have been observing and studying this particular galaxy. I would like to know all other data sets that looked at this galaxy because I would like to put together a multicolor, multi-temporal view of what this galaxy looked like. We also provide compute services for researchers, and really importantly for the volumes of data that we have now, automation. Because a powerful laptop is no longer enough to do the sorts of processing that needs to be done on the data volumes we have. So we provide a service for people and we provide some automation so that they only have to do the interesting bits, not the boring bits where you turn the handle. And we also provide platforms for data analysis. And then very importantly, we adhere to International Virtual Observatory Alliance principles. Until fairly recently, the chair of the IVOA was within the AAO, sitting over there if you want to ask about IVOA principles. And that international organization is all about making sure that any data that we take can then be taken by, sent to somebody in Europe, and they can do the same science that we would do here. It's all about making sure that the data are rigorous. Needless to say, those of you who know me, I am going to say that software and data engineering underpin almost every process involved in the advancement of modern astronomy. I say it because it's true. From the collection of telescope proposals, the control of telescopes, from driving the archives, simulating, processing data, it all needs software and data engineering. But fortunately, what we do is fundamentally interesting, often challenging, which is good, sometimes frustrating, but rarely, rarely dull. So Simon O'Toole and I lead the AAO's research data and software section, and our mission is to facilitate science and research across multiple disciplines. So we started in astronomy, and now we are able to say some of the techniques that we use in astronomy for the data can be applied to other research disciplines. And we're a team of software engineers, data scientists, IT specialists, and DevOps specialists as well, who work together to do this work. We are 23 people, which is a lot, but we also have a lot of work to do and a lot of expectations from the Australian community in particular to do all this work for them. So I'm going to end by showing you an image from the 3,200 megapixel LSST camera of the Rubin Observatory. This is the largest digital camera in the world. I'm going to say that again, 3,200 megapixels. Yeah? If you go to their website, I encourage you to go and find this image because they have a zoomable version. And you can go in there and zoom in to every little detail and you can see all these beautiful galaxies. So Australia is involved with work on the Rubin Observatory. Certainly we're involved from a data and software perspective, and Stuart over there is organising the project on Australia's behalf. And this observatory will scan the night sky every night for 10 years, creating an ultra-wide, ultra-high definition time-lapse record of our universe, if you like, in magnificent colour. So I'm going to stop there and thank you for your time.
Thanks a lot, Nuria, for a wonderful talk. We have time for some questions, and I'm going to ask my assistant here to also help hand out the mic. So we've got one at the back to kick us off. And I particularly encourage questions. The younger people in the audience. We know you've got the best, so don't forget to raise your hand.
For your excellent talk, it's wonderful. I'm just wondering, is spectroscopy limited to visible light then, or can you do it in the long and short wavelengths, the non-visible?
That is such a good
And can I just
question.
ask you, just as an added to that, the images you have in the infrared and the ultraviolet X-ray, how were they converted to visible images? How do you make it visible light? Thank you.
They're really good questions. Thank you for asking that. So yes, spectroscopy works across all of the wavebands. So the difference between visible and other colors of light is really only our ability to detect them. Not entirely. So the reason why radio telescopes look different to optical telescopes is because we need different materials to capture the light of that color. But that's really the only difference. And so in the radio, for example, we do a very similar thing. We produce data cubes, which are spatial in these two dimensions, and then the color is in this dimension. Sorry, the microphone's off. So the second part of your question, yes. So to allow us to see the colors in the non-visible ranges, we do put fake colors on. Or we use things like contours. So in that first image that I showed of the radio of the Sombrero Galaxy, rather than using colors, it used contours to show where the edges of the light was for the radio. Yeah.
Okay, I've got another question down here.
Thank you. Thank you for your beautiful talk, Nuria, quite literally and as a talk. I was wondering, how do you see AI impacting your work, or how is it already impacting it?
Yeah, that's a really interesting question. I think AI is part of our lives. We can't get away from it. So in the software and data space, particularly in the software space, we have used automation tools for a long time. So when I started in the field in 1993, there already existed some tools that helped you to not have to do all the donkey work of software. This is slightly different, but in concept, it's the same sort of thing. It's a tool which, if used well, we can do more of the interesting work and let the computers do more of the dumb work. The problem becomes when we expect AI to do the creativity for us. And particularly in the sort of work that we do, that's not really going to happen. You know, the people that are sitting over there, yes, they write really good code. Some of it could be written by AI eventually, but what it will not do is the creative part of the engineering. So yes, I encourage everybody to look at AI as a tool, much like you would use a thesaurus, but don't give away the spark that makes you human and creative.
And up at the back.
And so,
Oh, that's a really good question. I'm going to ask Amir, do you know how big the sensor is? Because I don't actually know. LSST cam.
The sensors altogether, the dimensions would be something between 0.5 and 1 meter, I think.
So between 0.5 meter and 1 meter. So it's not a single sensor, right? I should say. It's an array of sensors. And in terms of processing, a lot of this depends on what you're trying to do. So a lot of the processing from telescopes, because we're trying to find out things straight away, whether it's that there's a new transient object in the sky, or simply whether the quality of the observation is any good, or whether we need to take it again. We run what is known as a sort of a quality control pipeline, which is a very quick processing pipeline to give you a first look to get information about bright things, about problems, and so on. You then offline can spend days processing the data again to get the excuse me, to get the full depth, to get the maximum out of the data. So you can process the data in different sorts of ways.
And how long is the actual capture time of the photo?
This one, do I have the numbers? No, I don't have the numbers on me. But this will be multiple exposures that will be stacked together. Does anybody, any of my
I think
colleagues know?
it would be measured in minutes.
Each one 30 seconds makes sense, and then it will be some number of exposures stacked together to give us better dynamic range, so better signal to noise.
Okay, we've got a question down here.
Oh, sorry, I don't think the mic's on. Is there evidence that aliens exist? Really good question. It's not a funny question. I spent a long time when I was working in Narrabri at the Australia Telescope, looking after the MOPRA telescope that was part of the SETI program, looking for aliens. So thus far, no evidence, no hard evidence. And before any of you think, oh, but if there was, would you tell anyone? Because my dad used to say this to me. Every once in a while, he would say, if you saw aliens, would you just tell me, even if you weren't allowed? Astronomers are the sort of people who would not be able to contain it. Nobody's signed a non-disclosure on aliens. If there were some, you would know, because we would be writing papers about it. But maybe the question you're not asking is, do they exist? And we don't know. There are programs that are still looking, but probability says probably, because are we likely to be the only life in the universe? That's sort of big noting ourselves a little bit, isn't it? So probably, but are we likely to find them? That's really, really hard, because there are billions of star systems, and you would have to actually pinpoint the right one at the right time. So it's a really hard thing to do. But I think most astronomers would say probably they exist.
So I think we've got time.
Two more, just on the front. What is the shortest and longest wavelength that can be detected?
Oh, okay. The shortest and longest. Well, you can detect DC. So, anyone remember what Malonglo was? Sorry, I used to work in the radio, but I don't know what Malonglo did.
Well, it's the Murchison Linefield Ray goes down to 73 wavelengths, so that's like meters.
Yeah, that's pretty long. And the shortest would be gamma rays, so the gamma ray observatories. You know, we've covered pretty much the whole of the spectrum, because we're trying to find out how does the universe look in all the different energy wave bands, which are represented by those wavelengths. Often, what stops us from seeing a particular wave band is the technology, because the engineering is hard, working out exactly how to detect that light and how to transform it into data that we can then process.
And one last question down here.
So basically, does the material in the light bucket determine which wavelength of electromagnetic radiation gets passed into the tube?
Good question. So the bucket is about how many light particles can you catch? Because the more particles you catch, the fainter things that you can see. What determines the wavelength is the thing that you use as your reflector and what instruments you put in the back of it and what camera detector you put in the very, very end. So each of those things needs to be tailored for the color that you want, which is why radio telescopes don't have a mirror. I mean, they do, but it's a radio mirror, which to us just looks like a piece of metal, or even a piece of mesh if you're looking at long wavelengths of radio. And you know, the X-ray telescopes have a different reflecting surface that reflects X-rays, because of course an X-ray would mostly go through this. So everything's tailored to the particular color.
I'll remind you that you are free to come down and ask questions from Nuria once the talk is finished. But that was a wonderful talk, and I'd like you to join me in putting your hands together to thank Nuria for it. So if you've enjoyed this talk, I know I certainly did, I'll draw your attention to the next one in this series, which will be on the 16th of April by Dr. Cameron Edmond on weird little algos. Come and find out what that's all about. Thanks again for you all for coming out this evening. Feel free to hang around. There's some things here at the front if you want to chat with Nuria and have a look at it. And please safely home. Thank you.
Did we get both acetates back? Okay, cool. Turn that off. Hello.
I was interested in how the funding works for your data processing unit and how the pricing works for users wishing to access the facility.
So the pricing for users is free. So we do this as a service to the community, and you know, the public, you could set up a data center and download it later. You could do that.